In part 4 of section 18, we're going to be investigating a special type of exponential function called the natural exponential function. This is a special type of exponential growth. Now, this special type of exponential growth uses a very particular base. And what we're going to see here with example 18.8 is an exercise that we can go through that would help us to be able to develop this value for ourselves. The value that we're going to be coming up with is known as Euler's number. It is credited to Leonhard Euler. He is a mathematician from the 1700s. And Euler's number can be found on your calculator. It is represented by E. Euler's number is irrational, just like pi, but it serves a very different purpose than pi. So I want to walk us through an example here that's going to help us to be able to see the interesting competition that ends up creating this value. So there is a statement, an expression that was of interest at the time, and it's the expression 1 plus 1 over n raised to the n. You can see it right here in the second column of this table. And the interest was what's going to happen as we allow the value of n to get larger and larger in the positive direction. So let's start with a nice positive integer like 1. So if we were to plug in 1 into this expression, we would end up with a base of 2 and an exponent of just 1. And if we were to plug in a larger positive value, say 10, we would end up with a base of 1.1 raised to the 10. And at any point during the video, if you want to pause and then do these calculations for yourself, I encourage you to do so and see exactly where these values are coming from by plugging the appropriate value of n into the expression. Now let's go on to 100. If I plug in 100, I'm going to end up with 1.01 raised to the 100. If I were to plug in 1,000, I would have 1.001 raised to the 1,000. And this is the competition that I'm referring to. The base is getting smaller, but the exponent is getting larger. So what do we expect to happen to the result of executing this operation? Because we're going to have to take this base and actually raise it to the value that's here. So it brings up a really interesting question of what's more powerful, the exponent getting big or the base getting small. We can continue this pattern for ever because we're supposed to be allowing n to approach infinity. Now we won't have to do this forever because we're going to start to see a pattern emerge, and this is what eventually becomes Euler's number, is the pattern that we get from this. So let's go ahead and start with some calculations. 2 to the first power. Your calculator should just tell you that it's 2. In fact, you don't need your calculator for that one. But now we're going to start getting into some higher exponents. Next calculation, 1.1 raised to the 10th. I have that this is approximately 2.59374246. So we see an increase in the value of the expression when we go from an input of 1 to an input of 10. Now let's try the 100. So that's going to be 1.01 raised to the 100. This is going to be approximately 2.704813829. Let's try 1,000. That is going to be approximately 2.7169 23,932. And I already have some other calculations done here for the 10,000, 1 million, and then also 1 billion. 10,000 is going to end up being approximately 2.718145927. 1 million will be approximately 2.718280469, and then for 1 billion, getting on up there, 2.718281827. Now it's interesting to see that we still get a little bit of an increase going from the 1 million to the 1 billion calculation. But notice how far out we have to go into the decimals to actually see some change. We have to go all the way out here to the 1, 2, 3, 4, 5, 6th decimal place before we actually see the increase occur in that. Whereas if you look from the 10 to 100 calculation, just look at the first decimal place and you can see a change there. So as the value of n gets larger and larger, we're going to be getting a better and better picture of the pattern for this number. And this pattern, again, is called Euler's number. On your calculator, you should have a button that is E. And for a lot of calculators, it's going to be E raised to the something. And so to simulate E, you're going to have to input a 1 for the exponent. So that way you're just going to get e to the first power, which is e. And my calculator says that e is going to be approximately 2.718281828. So as I look at this answer compared to what I had here for the 1 billion input, the only difference is right here on that final digit. So we're getting a really good approximation to Euler's number with this table just by simply going out to 1 billion. So the limit statement that we can say is that the expression 1 plus 1 over n to the n is approaching Euler's number as n approaches infinity. Now, what throws a lot of students off is what we call this thing. Euler's number is an irrational number, but it is called, I'm going to put it in quotes, the natural number. Although it is not actually a natural number, it is called the natural number. And if I use the natural number as the base for an exponential function, that's going to create the natural exponential function, which is the title of this part in the section. And since Euler's number is greater than 1, we can expect this to be a growth model. So we're going to use Euler's number in an upcoming example to demonstrate what the graph of the natural exponential function will look like.